Can we start?
Yes, ma'am.
Okay, I will share the slides now. Is the slides visible?
Yes, basically.
Welcome back to NPTEL PMRF tutorials on Introductory Organic Chemistry 2, August 2023 to October 2023 by Professor Harina Chakrabani and Professor Neeraja Deshaputre. Myself Anisha Suresh, PMRF TA for this course from IIT Bombay. Today we will be discussing week 4 assignments from previous year. So do you have any doubt regarding week 3 assignment questions that we have solved? If there are no doubts, we can move to today's session. Today we will be discussing first a summary of lectures that are discussed in week 4, followed by we will be solving assignment questions from previous year. So coming to the summary of week 4, in week 4, sir have discussed ma'am have discussed regarding carboxylic acid and its derivative, followed by reactions of carboxylic acid and its derivative. Then a brief summary about alcohol ethers and epoxides. It is better to go back and see Introductory Organic Chemistry 1 for further knowledge about alcohols, ethers, and epoxides. Then a special topic, even CP reaction, was also discussed. Now, coming to carboxylic acid and its derivative, this is the structure of carboxylic acid, R C double bond O OH. If OH is substituted by any group like X, then it is called carboxylic acid derivatives. Some of the examples of carboxylic acid derivatives are acid chlorides, also known as acyl chlorides, then esters. If OH is replaced by OR, then it is called esters. Then acid anhydrides. If OH is replaced by C double bond O R, then it is called acid anhydrides. And if OH is replaced by any amines, then it is called amides. So these are the structures of carboxylic acid and its derivatives. Then we have seen the mechanism for the reaction of nucleophilic addition to carboxylic acid. So here uh, nucleophilic addition followed by substitution is taking place here. So here first formation of tetrahedral intermediates will be formed by attack of the nucleophile to this trigonal carbonyl group. This carbonyl group is trigonal planar because this carbon will be sp2 hybridized. sp2 hybridized carbons mostly show trigonal planar geometry. This is clear, right? So the nucleophile will be attacking at this carbonyl carbon, which is the electrophilic center. Then the CO double bond will be opening up, and it will result in the formation of this tetrahedral intermediate. So now the carbon center have changed from sp2 to sp3. Now what will happen? The oxygen will try to come back to its position, and this X, which could be any living group, it will be replaced, and it will result in the formation of product, which will also be trigonal planar because now the carbonyl carbon have formed, and again this sp3 have changed to sp2 hybridization. So this was the general mechanism of nucleophilic addition reaction on carboxylic acid and its derivatives. It follows a tetrahedral intermediate pathway. Now, how the mechanism was derived means, so for understanding the reaction mechanism, they have substituted the carbonyl oxygen with O18 isotope of oxygen. Then Upon reacting with this water is having lone pair of oxygen. It can add on to this carbonyl carbon, follow this reaction pathway, and replace this X group, resulting in the formation of this compound. So here there can be a rapid migration between this two O groups, like migration of this hydrogen atom between these two O groups. It can be through, like, so here double bond O will be forming and here OH will be forming. Now they have shown the mechanism here. H2O will be adding, this will be opening up, a tetrahedral intermediate will be forming. Now there can be a migration between the protons of these oxygen atoms. Here this H2O plus, one of the proton can be abstracted by this O18 oxygen, or both of this can be migrated between this O18 and normal oxygen. So two tetrahedral intermediates are possible. Now what will be the final outcome? So now the tetrahedral intermediate will be collapsing to give the carboxylic acid product. How? Like tetrahedral intermediate, this O minus will fall down and it will remove the leaving group, resulting in the formation of this uh, product. And upon removal of one proton, it will result in the formation of this carboxylic acid product. So here this oxygen will be O18 substituted one. And another possibility is, this it can also revert to unlabeled starting material. Our starting material was with labeled oxygen. So one other possibility is that when this oxygen will fall down, this water will be removing. It will be removed as H2O 18. So labeled oxygen will be removed and it will result in the formation of this starting material back without the O18 labeled oxygen. So these are the two possibilities. So this is how through labeling experiments that scientists mm, uh, come to a conclusion that these reactions go through a tetrahedral intermediate. Now the reactions of carboxylic acid and its derivatives. So we have for the reaction to take place, like nucleophilic substitution reaction to take place on this uh, carboxylic acid and its derivatives, what should be the condition? X must be a better leaving group than Y. We have seen that this should be removed for resulting in the formation of this product. Otherwise we will be getting the starting material back. So X should be a better leaving group. Y must be a strong enough nucleophile to attack RCOX. Y should be a good nucleophile. Nucleophile will be having negative charge. It will be attacking at the electrophilic carbon center. So nucleophile should be strong enough. RCOX must be good enough electrophile to react with Y minus. So this carbonyl carbon should be electrophilic enough so that it will be reacting with this Y minus. These are the conditions for reactions of carboxylic acid and its derivatives to take place. So this is the reactivity order of different carboxylic acid derivative. Acid chloride will be the most reactive, then comes anhydride, then esters, and then amides. We have seen the reason for all this in the lectures. So the electrophilicity at the center will be more, followed by this Cl will be a better leaving group. So this we have seen in the lectures. What will be the reason why acid chloride is more reactive and amide is least reactive? So this is the reactivity order of acid chloride to amide. Okay. Any doubts?
No doubt.
Okay. So then we have seen that acid chloride can react to give this anhydrides, esters, and amides through different reactions that are known. Then similarly, anhydrates can react to give esters and amides Then esters can react to give amides. So this is a summary of the reactions that can take place. Then carboxylic acid could be converted into uh, acid chlorides by reaction with SOCl2 or PCl5 or COCl2, COCl twice. So we have seen the mechanism of this in the lecture videos. If you are having any doubts, you can ask. Then carboxylic acid can be converted into esters by treating with alcohols in the presence of acids, and this ester can undergo hydrolysis in the presence of acid or base to give back the carboxylic acid. Then this amides can be converted into carboxylic acid by treatment of water in the presence of strong acid or strong base. Amides can be prepared from the reaction of acid chlorides, acid anhydrides, esters, etc. by reaction with ammonia. So I think the reaction summary chart is clear for everyone. So now we will move to alcohols, ethers and epoxides. So here the main reaction that was discussed was Williamson ether synthesis for the synthesis of ethers. Then we have discussed regarding how alcohols are formed, epoxides are formed, some reactions of alcohols, etc. Ma'am have discussed a summary of the uh, different reactions of alcohols, ethers, and epoxides and their formation reaction. So, better is to go back to Introductory Organic Chemistry 1 for seeing the detailed reactions of alcohols, ethers, and epoxides. So, what is the mechanism of Williamson ether synthesis? So, alcohol in the presence of sodium, it will result in the formation of RO minus, like a sodium alkoxide will be forming by releasing of hydrogen gas. Then this RO minus can attack to an alkyl halide, preferably a primary alkyl halide, because a SN2 kind of attack is taking place here. It will result in the formation of ether plus sodium halide will be removed. So mechanism of Williamson ether synthesis is clear for everyone.
Secondary light can also give
Hello.
ether. Can secondary halide can give
Yeah,
ether?
but reaction rate will be lesser. We have seen the like SN2 reaction order, right? So for primary, the reaction rate will be more compared to secondary. For tertiary, it will be least or it probably does not occur, right? So similar is the reaction order for Williamson ether synthesis also. Like alkyl halide, this alkoxide attack will be similar to that of SN2 reaction, backside attack. So the order will be primary greater than secondary greater than tertiary. So preferably primary alkyl halides are used for Williamson ether synthesis. Clear?
Yes, ma'am.
Now coming to even CB reaction. So this is the mechanism for even CB reaction. In this case, first the base will be abstracting the proton, resulting in the formation of enolate. So this reaction is a fast and reversible deprotonation. So this is a reversible step and it takes place at a faster rate. Now when the enolate will fall down, this double bond will shift to this side and this leaving group will be removed. So this removal of the leaving group will be the rate determining step of this reaction. So uh, if we are considering this as the acid, This will be the conjugate base, right?
Yes, ma'am.
By removal of proton, it will be resulting in the formation of a conjugate base. So this is the conjugate base of this acid. So this reaction is even with respect to this conjugate base, that is why it is known as even CB reaction. So this will be the rate determining step, and here only one substituent is involved. So if we are considering the rate equation, here the number of components or starting materials involved is only one. That is why it is known as even CP. So this was the mechanism of even CP reaction. It was a special topic that was discussed in week 4. Now for references, you can follow Claydon Organic Chemistry, chapter 12 for carboxylic acid and its derivative and their reactions. Then chapter 19 for elimination reactions. So even CP mechanism etc. will be discussed in detail in chapter 19. So this was a summary of week 4 lectures. If you are having any doubts, you can ask now, or else we can move to problem solving. Hope there is no doubts. So now moving to problem solving session. This is question number 1. Which of the following compounds is most likely to follow even CB mechanism when treated with C2H5ONA in ethanol? This is sodium ethoxide. In the presence of ethanol, which of these following compounds can undergo even CB mechanism? Like most likely. There might be more than one compounds that can undergo even CB mechanism, but which will be the most likely to follow even CB mechanism? Yeah, C can also undergo even CB mechanism as we have seen in the example, but B will be the most likely to undergo even CB mechanism because the anion that is formed, it can resonate into the phenyl like benzene system. Because of that, the anion will be more stabilized. So even CB mechanism is more likely to occur in this system. We can see the mechanism. So here this will be the acidic proton. Benzelic proton will be the acidic proton. So sodium, so ethoxide. So the ethoxide anion will be abstracting this acidic proton. So it will result in the formation of this anion. So this anion can resonate in this whole system as we are seeing here. So this will be the first step of even CB reaction, which is the fastest step. Now the slower step, that is the elimination step or halide removal. It will be taking place like the anion will be falling in this direction. This double bond will shift in this fashion. This double bond will shift into this side. This double bond will shift into this side, and this bromide, which is a leaving group, will be removed. It will result in the formation of this product. Is this clear? Why we choose this compound over this? Is that clear?
Yes, ma'am.
Because in the benzylic system, the proton or the anion that will be forming, it will be more stabilized. So the most likely compound to undergo M1CP mechanism will be this benzylic bromide kind of system. Now coming to question number 2. Is question number 1 clear to everyone? I hope it is clear. Now coming to question number 2. Identify the major product formed in the following reaction. Here an alcohol is given and butyl. N-butyl bromide is given. It is treated with NaOH in the presence of ethanol and heated. So it will result in the formation of some product plus NaBr plus water. So what will be the likely product that will be formed in this reaction? So four options are given. What is the major product?
Option A.
Option
First,
first
option
option.
one.
Yeah. Option 1 will be the right option. So we will see the mechanism of this reaction. So NaOH, this OH minus hydroxide will be abstracting the proton from this alcohol and result in the formation of this alkoxide. So this alkoxide can attack this alkyl halide or butyl bromide in SN2 fashion. Bromide will be removed and it will result in the formation of this product. Mechanism is clear and simple, right? Any doubts? So the right answer will be option A. NaOH will be attracting this proton, followed by the anion will be attacking in SN2 fashion to this alkyl halide. It will result in the formation of this product. Hello? Anyone having doubts? Any doubts?
No.
Okay. Now coming to question number 3. A chemist carried out a Fischer esterification using methanol that was isotopically labeled with O18. So this O18 is indicated by this asterisk symbol. So identify the product after the reaction. So Fischer esterification, which is used for esterification of this carboxylic acid, it was carried out using isotopically labeled methanol. So this methanol is isotopically labeled with O18. So what will be the product?
Second ester.
Second one. This will be the right answer. We will see the mechanism for that reaction. So here this methanol will be attacking at this carbonyl carbon, which is the electrophilic center. It will open up, resulting in the formation of this tetrahedral intermediate. Now, like a proton transfer can take place. Here a proton transfer can take place between this CH3OH and OH. So it will result in formation of this tetrahedral intermediate. So now when this OH lone pair of oxygen will fall down, this H2O water will be removed, resulting in the formation of this compound ester, and water will be removed. So this after deprotonation, it will result in the formation of this ester. Any doubts in the mechanism? anyone is having doubts, you can feel free to stop and ask. Any doubts? So the correct answer will be option B, where this oxygen on the methanol. Oxygen that was present on the methanol will be remaining on this, like whatever nucleophile was added. Can we move to question number 4?
Yes, ma'am.
Yes, ma'am.
Okay. Now this is question number 4. Which of the following acids have the smallest dissociation constant? Dissociation constant is Ka. We might have seen pKa. So pKa is the negative logarithm of Ka, and K pKa we were using to find the uh, which acid will be more stronger. For finding out that, we were using pKa. So what will be the correct answer? Which of the following acid has the smallest dissociation constant?
Option 3.
Third option.
Third option. Yeah, that is the right answer. So we will see first what is Ka once again. So the acid dissociation constant Ka is used to distinguish between strong acids and weak acids. Strong acids will be having higher Ka values. We have seen that lower the pK, stronger the acid, right? So pKa is the negative logarithm of Ka. Because of this negative symbol, this trend is coming. If pK is lowering, acid will be stronger. So Ka should be more for stronger acids. Ka value is found by looking at the equilibrium constant for the dissociation of acid. So higher the Ka, the more the acid dissociates. So Ka is found using this equation, where K equal to concentration of H plus into concentration of A minus divided by concentration of Ha. So if concentration of H plus increases means it will be a stronger acid. Stronger acid will be deprotonating more. So if K increases, the acidic strength will increase. So out of this four option, the strongest acid will be which one? Which one will be the strongest acid?
First one.
Yeah, this will be the strongest acid. Then
Second.
it will be fourth one, because sorry, because this fluorine is present in the, like, one carbon away. This fluorine is present one carbon away. So the inductive effect because of this fluorine will be lesser, right? This will be coming third, and this will be coming fourth. So by the electron withdrawing inductive effect of this fluorine, the conjugate base that will be formed by this acid, that is COO minus F, it will be stabilized. The negative charge intensity on this base will be reduced by this electron withdrawing inductive effect of this fluorine. So this electron withdrawing inductive effect will decrease as we move further away from this carboxylic acid. So here fluorine is a strongly electron withdrawing group. Because of that, uh, this fluorine can stabilize the CO minus more. So next, this is also an electron withdrawing group, bromine. So this is present on the adjacent carbon. Because of that, it can stabilize this CO minus more. Then comes this fluorine because it is present one carbon away from this carboxylic acid. Because of that, the inductive effect will be lesser. So this will be having third position in case of acidity, and this will be having fourth position in case of acidity. So if you are asked to arrange in the order of acidity, it will be A greater than D, greater than B, greater than C. So we have seen A is a stronger acid. So it will be having greater dissociation constant. Stronger acid will be having greater dissociation constant. And C is the least acidic among the given options. So it will be having the smallest dissociation constant. So if we are able to see which is more acidic among the given groups, then we will be able to predict about the dissociation constant of that given compounds. You are clear about how I have found which is a small which of the acid is having smallest dissociation constant, right? Any doubts?
नो मैम। अरे ये सोया है क्या? तू आज चलनी नहीं? अगर चलनी नहीं तू आज?
Nilima, any doubts?
नो मैम, नो मैम।
Okay. So the correct answer will be option C. Now coming to question number 5, the formation of cyanohydrin from a ketone is an example of. So we are having a ketone R double bond O R. So it is reacted with a nucleophile Cn minus. It will result in the formation of, so this is called a cyanohydrin. So this is an example of what kind of reaction? Is it electrophilic addition, nucleophilic addition, nucleophilic substitution, or electrophilic substitution?
Nucleophilic addition.
Yeah, this is an example of nucleophilic addition because the cyanide, that is say nucleophile, it is attacking on this electrophile, and this is an addition. This Cn minus is getting added to this ketone. So because of that, it is an example of nucleophilic addition reaction. This is clear for everyone.
Yes, ma'am.
Okay. Now coming to question number 6. By reacting with Grignard's reagent, other aldehydes than formaldehyde produce additional product that include tertiary alcohols, secondary alcohols, primary alcohols, carboxylic acid. So here what they are asking is, except formaldehyde, other aldehydes will be giving what kind of product? So what will be the answer? So you are familiar with
Secondary alcohol.
yeah, secondary alcohols is the right answer. Grignard's reagent will be RMgX. So when it is reacting with formaldehyde, first we can say that what will happen. So formaldehyde is HC double bond O H. So RMgX, here the magnesium will be having delta positive charge, and this uh, R group will be having delta negative charge. So it will be attacking on the carbonyl center. This will be opening up, and it will result in the formation of OMgX. and it's upon hydrolysis it will result in the formation of RCH2OH. So this will be a primary alcohol. Formaldehyde, upon reaction with Grignard's reagent, it will result in the formation of primary alcohol. So now what will happen with other kind of aldehydes? So for other aldehydes, one of the hydrogen of the formaldehyde will be replaced by an R group. Then if it is reacting with this Grignard's reagent, here this R dash will be having delta negative and this will be having delta positive. R dash will add to this electrophilic center, that is the carbonyl carbon. Upon adding, it will result in the formation of this compound, and this upon hydrolysis, that is treatment with H3O plus, it will result in the formation of ROH R dash. So this is a secondary alcohol. Mechanism is clear, right? Any doubts?
No doubt.
Okay. So the correct answer is, by reacting with Grignard's reagent, other aldehydes than formaldehyde produce secondary alcohols. Now coming to question number 7. Identify the intermediate X and product Y in the following reaction sequence. Here this methyl magnesium bromide, that is methyl Grignard reagent, it is treated with carbon dioxide in presence of dry ether. Then, upon hydrolysis, it will result in the formation of some product along with MgOH which is a byproduct. So, what will be this intermediate X and what will be the product Y?
First option.
Yeah, option A will be the right answer. So, we can see the mechanism. So, the CH3MgBr, here this will be having delta negative and this will be having delta positive charge. This delta negative CH3 minus will be attacking on the carbon atom of this carbon dioxide. It will result in opening of one of the C double bond O bond, and it will result in the formation of this intermediate CH3 double bond O minus MgBr plus. Here MgBr plus was there. This O minus will uh, form an ionic bond with that. Then, in the presence of H3O plus, this O negative of this will be abstracting the proton, and this OH will H2O will be removed. So, we will be having acid and MgOHBr as the byproduct. Any doubts?
No, ma'am.
Okay. So, the right option was option A. Now coming to question number 8. Predict the final product of the given reaction. So here benzoic acid was treated with AgOH, silver hydroxide, and it was treated with allyl bromide. So what will be the product?
Option C.
Option C is the right answer. It will result in the formation of ester. So we can see AgOH, this hydroxide will be abstracting the proton from this carboxylic acid. This proton will be more acidic. So AgOH will be abstracting that proton and it will result in the formation of this benzoate, this carboxylate anion. So that will add on to this allylic bromide. So this double bond will shift in this direction and this bromine will be removed. It will result in the formation of this ester moiety. Mechanism is clear?
Yes, ma'am.
Okay. These reactions all are like similar. If we are understanding like what is happening with the if we are understanding the reaction mechanism of one of the derivative of carboxylic acid, we will be able to solve most of the questions. So the right
Can
option.
we eat other bases other than silver hydroxide?
What?
Can we can we use in this reaction other base
Yeah, you
rather than
can use
silver
other
hydroxide?
bases. You can use other bases.
Okay.
So the right option was option C, which is this ester. Now coming to question number 9. An ether is more volatile than an alcohol having the same molecular formula. This is due to A. Dipolar character of ethers. B. Alcohols having resonance structures. C. Intermolecular hydrogen bonding in ethers. Intermolecular hydrogen bonding in alcohols. So ether is more volatile than alcohol. That means boiling point of ether is less than that of the boiling point of alcohol. What is the reason for the same?
Option 4.
Yeah, intermolecular hydrogen bonding in alcohols. So alcohols will be having R O H. So like it can result in hydrogen bonding. Because of this hydrogen bonding interaction, the boiling point of alcohols will be more. In case of ethers, there is no hydrogen atom that can do hydrogen bonding. Because of that, ethers will be more volatile than the acid. Sorry, alcohol. Clear? Alcohols will be having oxygen and hydrogen which can undergo hydrogen bonding interaction. Because of that, alcohols will be having a greater boiling point. But in the case of ethers, there is no hydrogen atom that can undergo hydrogen bonding interaction. Because of that, the boiling point of ethers will be lesser. Hence, they will be more volatile than alcohols. Clear, right? So, the intermolecular hydrogen bonding in alcohols is the result why ether is more volatile than an alcohol. Any doubts? Hope this is clear. Now, coming to question number 10. The major organic product Q formed in the reaction given below is. So here this ketone is treated with diazomethane. So we will get an intermediate P, and that is treated with ethanol in the presence of sulfuric acid. So what will be the product Q that will be forming here? So any idea?
Option D.
Option B. Yeah.
4, ma'am.
Huh?
Second option.
Yeah, second option is the right option. We will see the mechanism for this reaction. So we have seen in the lecture videos this diazomethane will be having this structure, a negative charge on the CH2 and this positive charge on the nitrogen. So this is a neutral molecule, but here there is a negative charge on this CH2. So it will be adding on to this carbonyl carbon of this ketone. then this oxygen will open up. Now what will happen? So we will get an tetrahedral intermediate. Now what will happen? This oxygen will add on to this carbon where this N triple bond N is attached. Then this nitrogen molecule will be removed. We know that nitrogen is a good living group. So this is what is driving the reaction. So here there is a possibility of removal of the nitrogen atom. So because of nitrogen molecule, so because of that, this O minus will add on to this carbon and this nitrogen gas will be removed. Will result in the formation of this oxygen. Clear? Mechanism is clear till this? Any doubts?
Ma'am, whether the hydroxyl group is substituted by ethanol or not?
This is added later after the formation of P. This is the second step, right? So first step will be
Okay, ma'am.
treatment with diazomethane. So we will get one intermediate. After the formation of the intermediate, that intermediate is being treated with ethanol in presence of sulfuric acid. So it is not in one pot. As two separate steps we are doing. Clear?
Clear, ma'am.
Okay. Now we are having ethanol in presence of sulfuric acid. So because of the presence of sulfuric acid, this oxygen on this oxyrane will be protonated. Now this ethanol oxygen group will add on to this position and this will be opening up. So it will result in the formation of this product. Clear? So this is CH3, C, CH3, OET, CH2, OH. The product will be, there will be a chiral carbon. Sorry, it is not a chiral carbon because CH3s are same groups, right? So there will be a central carbon where it will be substituted with two CH3s, one CH2OH and one OET. The mechanism is clear to everyone, right? I think this is the only tricky mechanism that is in this uh, whole problem set that we are discussing. Any doubts regarding this question? Any doubts regarding the mechanism?
No, ma'am.
Okay. So the correct option will be option B. Now coming to question number 11. The relative reactivities of acyl compounds towards nucleophilic substitution are in the order of. We have seen the reactivity order of the carboxylic acid derivatives when we were discussing the summary of week 4. So I think it will be easier for you to answer this question. So what will be the relative reactivities of acyl compounds towards nucleophilic substitutions? So for option A, acid anhydride greater than amide greater than ester greater than acid chloride. Option B, acid chloride greater than ester greater than acid anhydride greater than amide. Option C, acyl chloride greater than acid anhydride greater than ester greater than amide. And option D, ester greater than acyl chloride greater than amide greater than acid anhydride. So what is the right answer?
Option C.
Option C is the right answer. As we have seen in the um, summary that we have discussed, acyl chloride will be more reactive than acid anhydride. Acid anhydride will be more reactive than ester, and ester will be more reactive than amide. So the correct option is option C. Any doubts?
No, man.
Okay. Now coming to question number 12. Predict the product of the following reaction. So here we are having an anhydride. It was treated with ethanol and heated. So what will be the product that will be forming in this reaction? They have given four options. So what will be the reaction?
Option D.
Option D is the right option. So coming to the mechanism, so this ethanol, it will add on to the carbonyl carbon. It can add on to any of this carbonyl carbon. Both are equivalent. So ethanol will add on to carbonyl carbon, and this CO bond will open up. It will result in the formation of this tetrahedral intermediate. Then a proton transfer can take place between this OHET and this O group on the ring. After that, now this lone pair of oxygen on this alcohol, it will fall down and it will result in the opening of this ring. So now we have got one acid and one ester. So this after deprotonation, it will result in the product that we have got. Mechanism is clear, right?
Yes, ma'am.
Okay. So the right option is option B. Now coming to question number 13. In which case would a Williamson ether synthesis fail? So here all the like bases or the starting material is the same.
Option D.
NaOET, and here this option D. Yeah, here the only difference is with the alkyl halides. So here CH3I, CH3CH2I, 2-iodopropane. So CH3, CH, CH3I, 3 2 methyl propane. CH3, C, CH3, CH3I. So as we have discussed when we were seeing the Williamson ether synthesis mechanism, as it is shown here, this alkoxide will be attacking the alkyl halide from the backside, resulting in the formation of ether and sodium halide as the byproduct. So this is an SN2 type of reaction, and the order will be primary greater than secondary greater than tertiary. So if we are having primary alkyl halide, the reaction will be most facile. Secondary halide, it can happen, but this facility will be decreasing, feasibility will be decreasing, and tertiary halide, it will be the least facile. So here this 2-iodo-2-methyl propyne, it is a tertiary alkyl halide. So because of that, in this case, this Williamson ether synthesis can fail because it is a tertiary alkyl halide. Clear?
Yes, ma'am.
Now coming to our, so the correct option for this question 13 was option D. Now coming to the last question, among the following esters, the one that undergo acid catalyzed hydrolysis fastest is, which of the following esters will undergo a fastest acid catalyzed hydrolysis?
Option B.
Option B is the right option. Now coming to like the reason behind this, so we can see this is the mechanism of acid catalyzed ester hydrolysis. So first protonation of this ester will be taking place. After that, water will nucleophilically add to this carbonyl carbon. It will open up, resulting in the formation of this tetrahedral intermediate. Now, what will happen? A proton transfer can be taken place between this OH. First, water will be deprotonating this OH2 plus. It will result in the formation of this tetrahedral intermediate, and it can protonate this OR dash. A proton transfer is taking place here. Now what will happen when this oxygen lone pair will fall? This OHR alcohol will be removed, and we will get this product with protonated oxygen. Then water will remove this proton. A deprotonation will be taking place, and we will get a carboxylic acid. But all this are reversible. You can see the reversible arrow. Carboxylic acid will convert back to ester as well. We should, if we are removing the like alcohol from the system, then it alcohol which is the byproduct, then it will be more, this reaction will move forward, resulting in the formation of carboxylic acid more. Now, what are the factors that will increase the rate of acid catalyzed ester hydrolysis? So, the factors are one, the electrophilicity of the carbon atom. If the carbon atom is more electrophilic, then the water can come and attack at a faster rate. And the nature of the living group. Then the ester, which is the living group here. It should be a better living group. Like it should be stable, so that it should be stable by itself, so that it will be removed, it will be a good living group. If the ester that is getting removed, or alcohol that is getting removed, is more stable, then it can have good living group ability. Clear? One will be the electrophilicity of the carbonyl carbon. So electrophilicity of the carbonyl carbon, it can increase if there is presence of electron withdrawing groups on the system. Then nature of the living group will be this alcohol. ROH will be the living group in this case. So if the living group is like more stabilized by its own, then it can be a better living group. So these are the two factors that are affecting the overall rate of hydrolysis reaction. So as we have seen, this is the ester that will undergo a fastest hydrolysis. We can see why. So here there is a phenyl group. It will be electron withdrawing in nature. If a hydroxyl group is present at the ortho position of the phenol, it will be more electron withdrawing compared to that in the meta position, right? If hydroxyl is present on this phenyl group, its electron withdrawing ability will be increasing. So the carbonyl carbon will be becoming more electrophilic. And if CH3 is present, then it will be electron releasing in nature. If it is electron releasing in nature, the electrophilicity of the carbon will be decreasing. The delta positive charge will be decreasing because of the electron releasing CH3. So here the carbon is less electrophilic. So we have seen that for the acid catalyst hydrolysis to be fastest, the electrophilicity of the carbonyl carbon should be more and the leaving group should be more stabilized. So this the leaving group here will be first case it will be OH. If there is negative charge even in this group, it can undergo hydrogen bonding. So because of that, this will be more stable living group. Okay, there can be hydrogen bonding interaction for this group, for this living group. Because of that, it can be more stable as well. So these are the reasons why this ester can undergo a faster acid catalyzed hydrolysis reaction. Any doubts?
No doubt.
Okay. So this was the last question of today's session. I hope all the questions are clear for you. So some of these questions are repeated in this year's assignment as well. So you can follow this video for solving those questions. But I think you have got the concept so that you can solve it yourselves. Most of the questions I think are easy questions for this week. If you are having any doubts, you can feel free to contact in the comment section of the YouTube channel. Any other doubts? You can follow chapter 12 for carboxylic acid and its derivative from Claydon textbook, and chapter 19 for even CB reaction mechanism. So thank you all.
Thank you.
Thank you, ma'am.
Thank you.